The reality you perceive around you, this solid three-dimensional universe, seems like the most fundamental thing that exists. And yet, many, perhaps most, physicists today think that space itself emerges from something deeper. And the most astonishing hypothesis is that our universe is nothing more than the projection of a two-dimensional foundation, infinitely distant. In other words, a hologram. I know, it seems impossible, but instead, it is a solid scientific theory supported by a significant part of the scientific community. In this video, we will analyze this hypothesis together and its implications regarding the true nature of our reality. If these questions fascinate you and you want to explore the deepest mysteries of the cosmos with us, do one simple but fundamental thing for us. Subscribe to the channel and click the bell. The work of physics is to discover the fundamental building blocks of reality, the so-called ontological primitives from which everything else emerges. For centuries, we thought that space was one of these, the foundation on which to build the universe. But today, this certainty is wavering. The idea that space is an emergent phenomenon is gaining more and more ground, and its most radical manifestation is the holographic principle. The story of this revolutionary idea began in a surprising place, with the study of black hole thermodynamics by Stephen Hawking and Jacob Bekenstein. Thermodynamics usually describes the behavior of systems with many particles, like gases, and one of its key properties is entropy. We can think of entropy as a measure of the hidden information in a system. A room full of air has high entropy because the positions and velocities of all the individual molecules are hidden behind the few properties we perceive, like temperature and pressure. A black hole, being the result of the collapse of an enormous amount of matter, hides within it a gigantic amount of information. Bekenstein and Hawking discovered how to calculate its entropy, and here came the surprise. The entropy of a black hole is not proportional to its volume, as intuition would suggest, but proportional to the area of its surface, the event horizon. It's as if all the information contained in the three-dimensional volume of the black hole could be written on its two-dimensional surface. This result, known as the Bekenstein bound, suggests that black holes represent the maximum possible information density in any volume of space. This led physicists like Gerard to Hooft and Leonard Susskind to take a step further. What if this didn't apply only to black holes, but to the entire universe? The holographic principle suggests precisely this, that the three-dimensional universe we call the bulk can emerge from the dynamics that unfold on its two-dimensional surface, the boundary. But how can an extra dimension emerge from nothing? The first concrete example of how this could work was given to us by Juan Maldacena with his famous ADS-CFT correspondence. Although this correspondence describes a type of universe different from ours, it is a very powerful tool for exploring the holographic idea. The CFT part stands for conformal field theory and describes the physics that occurs on the two-dimensional boundary. A key characteristic of these theories is that the physical laws are the same at any scale of magnitude. Let's imagine our two-dimensional surface as composed of many pixels of Planck length. On this surface, there can exist configurations of pixels on a small scale, but also larger, grainy configurations that extend over multiple pixels. Since the physics is the same at every scale, we can think of each scale of configuration as a level in itself. Now, we associate each scale with a position along a new dimension. The larger and grainier configurations we position near the center, the smaller and more detailed configurations more externally. If the separation between these levels is small enough, we have just created a three-dimensional space starting from a two-dimensional surface and from one of its internal properties, the scale. This brings us to a crucial philosophical question. Is the relationship between our 3D universe and its 2D description a true duality, where neither is more fundamental than the other? or an approximate duality, in which our 3D world is truly an emergent phenomenon? The truth is, we don't know. Furthermore, comma. It must be said that the idea of a non-fundamental spacetime is not just a quirk of the holographic principle. It resonates deeply with many other aspects of quantum physics. Phenomena like entanglement, where two particles remain connected instantly regardless of distance, or superposition of states, seem to violate our classical conception of space and locality. Perhaps these phenomena are not strange, but are clues that suggest to us the true nature of reality, that space as we perceive it is a construction that emerges from these deeper and non-local quantum connections. And this leads us to the final reflection, the most dizzying one. If we live in a hologram, what does it mean for our consciousness? If everything we perceive, this world, our bodies, other people, were nothing but a projection, what would become of our subjective experience? Our thoughts, our emotions, our sense of being, are they real, or are they simply part of the holographic illusion? This would radically change our conception of life. And comma, inevitably, of death. Is the information that defines us simply erased, or does it somehow return to that level of fundamental reality, to that surface from which everything originates? We have no answers. But these questions, born from the mathematics of black holes, push us to the boundaries of physics, philosophy, and our very understanding of what it means to exist. Thank you for traveling with us to the boundaries of knowledge. If this video has stimulated you and you want to continue exploring the great mysteries of science, I invite you again to subscribe to the channel. Until next time.